Semiconductors and band theory. So we've talked about the electron C model for metallic bonding. Band theory is a more comprehensive model. It grew out of molecular orbital theory. Do you remember which one of those things we talked about was molecular orbital theory?
Nope.
No. That was the one with the little boxes, and we stuck them in the middle, and we drew all the lines, and there's the antibonding and the bonding orbitals. Oh, yeah, right. Okay, the good news is we really just had to kind of introduce you to that so you could understand band theory, but we're not going to draw any more of those boxes, really, okay?
Wait, for the exam? Or?
For the rest of this lecture.
Oh. So it's going to be on.
There will be molecular orbitals on the exam, yes. Not much, but a little bit. So atomic orbitals are the orbitals on atoms. When you combine atoms together into a crystalline solid, those atomic orbitals overlap. They form the molecular orbitals that are delocalized over the entire crystal. So in some senses, a crystal is really one very, very large molecule. When those atoms combine and form molecular orbitals, we've got bonding orbitals with lower energy and anti-bonding orbitals with higher energy. The bonding orbitals will be occupied, the anti-bonding orbitals will be empty. As you get more and more atoms in this crystal molecule thing that we've got going on, the energy difference between those levels becomes negligible. So let's look at this illustration. So here's a lithium atom. So lithium has one valence electron. There's its one valence electron. It would be in the 2s atomic orbital. If you put two lithium atoms together, we're going to make a bonding orbital and an anti-bonding orbital. One electron from each atom, they're going to go into the bonding orbital. We can add 3. I don't like talking about that one. We'll add 4. 4 atoms. Now we've got 2 bonding orbitals, 2 anti-bonding orbitals, total of 4 electrons. You can go on and on and on and keep adding, and eventually the molecular orbitals get so closely spaced that they merge into what we call a band. So this is a band of orbitals. There's the bonding ones and the anti-bonding. The occupied orbitals are the bonding orbitals. We call this the valence band. That's where the valence electrons are. The empty orbitals are the anti-bonding orbitals, just all merged together. That's called the conduction band. Okay? Everybody okay with that? So electrons become mobile when they move from the valence band into the conduction band. So here in the valence band, this is full of electrons. It's like a crowded, congested highway. You know, traffic has come, it's just stop and go, nothing's really moving here. The conduction band is like either the carpool lane, but that doesn't even work very well anymore. It's more like the shoulder of the highway, right? You're not really supposed to go over there, but if you go over there, you've got a clear path and you can travel very easily, right? So what happens is some electrons will move into the conduction band and then they're mobile. They're available to conduct electrical current. In metals, there's no gap. There's no gap in energy between the valence and conduction bands. And so the electrons can very easily move into the conduction band and shoot down the highway. Making this up right now, I hope this works out okay. But so in metals, really, there's no penalty. You know, the police officer's not going to pull you over if you move over onto the shoulder and drive on the shoulder. So that makes medicals, metal electrical, medicals? I made up a new word. Metals are good electrical conductors because the electrons can move into the conduction band and move around. They also conduct heat very well because of the same thing. Electrons also have thermal energy. And so if you've got your more energetic electrons going into the conduction band and traveling around the surface or the substance, then they're also going to transmit that, they're going to spread around the thermal energy as well. So here we have conductors like metals. There's no energy gap. There's no penalty for going and driving on the shoulder. in a semiconductor, there's a small energy gap. So if you drive on the shoulder, you might get pulled over and get a ticket, but it's like a $20 ticket, and it's like, yeah, I think it's worth it, right? So you'll just do that anyway. In an insulator, there's a large energy gap. That's more like real life, where it might be like a $240 ticket or something like that. I don't know, I've never done that, but you violate the law, you go over there, something bad's going to happen. These are not going to conduct electricity. This gap is too big. Semiconductors, it's a small energy gap. Some electrons are going to have enough energy to be able to jump up there and move around. The conductivity of semiconductors varies with the temperature. As you heat them up, more electrons have enough energy to get into the conduction band, and the semiconductor becomes more electrically conductive. This makes them really useful as temperature sensors. So the metal electrodes, the metal temperature probes we have for the verniers, remember the lab quests we used on last week with the paper around them? Yeah. So those most likely have some sort of a semiconductor in the tip. As the temperature increases, they conduct electricity better, and so they can be used as thermometers. If you go down a group of elements, such as the group 4A elements, carbon, silicon, germanium, tin, and lead, the band gap decreases and the conduction increases. And this has to do with atomic radius. When we're talking about carbon here, we're talking about the diamond form of carbon. So as the atomic radius increases, then the overlap between the orbitals is not as efficient, and the energy difference decreases. So we see that lead and tin are metals and conduct electricity quite well. The band gap for tin is very small. It does have a band gap, but it's very small. Lead has no band gap. Germanium and silicon are semiconductors. They have small band gaps. Diamond is an insulator. It's not conductive. It has a large band gap. So any questions about that? Now we're going to talk about dope. Doping. Just waiting for the train. Okay. Doped semiconductors have small amounts of impurities. So you take a semiconductor and you add a substance that either has more valence electrons than the semiconductor or fewer electrons. And so this, if you're adding extra electrons, those electrons will have to go into the conduction band. The valence band is full. If you add something that has fewer electrons, you're going to end up with holes in the valence band. So there are two types of semiconductors, N-type and P-type. The N-type semiconductor has extra electrons, and it's called N-type because the charge carriers are negatively charged. They're the electrons. So if we take silicon in group 4A, it has 4 valence electrons. Those fill up the valence band. And we add in phosphorus. Phosphorus is in group 5A. It's got 5 valence electrons. So each phosphorus atom that's put into this semiconductor adds 1 electron. The valence band is full. That electron has to go into the conduction band. That electron is mobile and can conduct electricity. So the more of this you add in, the more conductive the semiconductor becomes. The other type is a P-type. And it's called P-type because we think of this as a positive charge that's mobile. It's really the absence of electrons, or an electron. So again, with silicon, if you dope it with gallium, gallium's in group 3A, 3 valence electrons. So now the valence band is going to have a hole in it because the gallium atom only brought 3 electrons instead of 4 like the silicon had. So there's a hole. The electron next to it can move into the hole, creating a hole behind it, and then the next one can move in. And so you've got this shuffle effect. And so you can think of that as the electrons moving or as the holes moving in the opposite direction. That's why it's called a P-type. So you can adjust the conductivity of the semiconductors by adding other materials in. Silicon chips, which have become very, very important in our everyday lives, have millions of p-n junctions. And those junctions are little tiny spots. They're p-type on one side and n-type on the other. And those junctions can act as diodes or as amplifiers. A diode is something which allows current to flow only in one direction. An amplifier will take a small current and make it into a larger current. And those are at the heart of all computer devices. So, any questions? So which element would you dope into germanium to create a p-type semiconductor? So a p-type, are we adding something with more electrons or fewer electrons? Fewer electrons. So germanium is in which group? 4A. It's in group 4A. So it was starting out to be Roman numeral 4, and then anyway. So it's got 4 valence electrons. So we want something with fewer valence electrons, so we're looking for group 3A, right? Which of these is in group 3A? Indium. So this is in group 3A. It's got 3 valence electrons. That's going to leave holes in the conduction band. In the valence band. What if we wanted to make an n-type? We'd add arsenic. Adding tin isn't really going to do anything in terms of changing the conduction because it's got the same number of valence electrons. Any questions?